Okay, so our final topic is molecular shape, which we also call molecular geometry. I kind of mentioned this in the last video. The nice thing about Chem 101 is that when you draw a Lewis structure with their program, it actually creates a geometry. So what we're going to be doing here is just kind of making sense of the way that they show those structures because we have to be able to interpret them and actually see what it means, okay? The molecular geometry is just the three-dimensional structure. It's how the atoms in a molecule spread out in 3D space to take up a room around the central atom, okay? And so the theory that we use that develops those structures is called valence shell electron pair repulsion theory, which we sometimes either say VESPR or VSEPR theory, okay? And it's a really simple idea. The idea is that bonds are negative, lone non-bonding pairs are negative, negative things don't like to be near each other, so those charges spread out to maximize their distance, right? So what we're going to have to learn is, right, how that spreading out occurs. Now, what matters is how many things are around a central atom. That's what it's all about. How many lone pairs you see on a central atom, we're going to reference those as E, all right? And I know it's a little bit confusing, but like I said, it'll be reinforced as we go through the video. Atoms that are attached have a bond or a multiple bond attached to it, okay? Each atom is bonded to that central atom. We're going to refer to those atoms as X's, or there's going to be an X number, right? Remember, it's not the number of bonds attached, because if an atom is attached with if an atom is attached with a single bond, or an atom is attached with a double bond or a triple bond, that's still just negative charge, all right? So what matters is, okay, if an atom is attached, there's negative charge there. The lone pairs in the atoms are going to want to spread out as far as they can, all right? We take the E and the X and we get what's known as an AEX designation. And the E is just really kind of the A is really just standing in for essential atom. And you'll see this in our general structures that we write. A stands in for the central atom, and then we see how many lone pairs are around it, how many atoms are attached to it, and that gives us a way of drawing these structures. Now, everything you need to know about geometry is all encapsulated in figure 7.19 in your book. Okay? Literally everything is there. So, because you can use your notes for things like the final, I recommend just copying down this figure into your notes. Okay? And actually, in copying it down, you'll see that you'll learn a lot about how to draw these structures. And I'm going to go do this with us as well. Okay? But having it in your notes is great because that figure is everything, okay? When you look at that figure, what you'll see across the top is there looks like like you have on the left-hand side a structure that's modified based on the number of E's. So the way we present this is we replace a structure that just has atoms attached to it, and then we modify that structure by replacing atoms with E's. The only thing that I would really change about the figure, the only thing that I don't like, is the left-hand column. It says something about electron pairs. I think that is better labeled as negative regions. So don't think about it as just pairs, because sometimes we have multiple bonds attached to a single atom. Literally all we're going to look at is how many E's, how many X's. That'll put us to a correct structure on this table. Okay, so to see how this works, let's go and let's look at some Lewis structures that we've already done together in our last video. And let's try to make sense, all right, of their geometry, of their actual structure, okay? So if we look at a structure like N2, all right, or O2, we know what these guys look like. This actually isn't on that chart because it's so easy, all right? Whenever you just have two things attached to each other, there's only one structure that's possible. There's nothing you can do to really take these and make them far away from each other. These guys are bonded, there's nothing to spread out. And remember how we had to like make up a central atom? We had to pick one of these as a central atom. Whenever two things are attached to each other, we know for sure it is linear, right? This picture is actually the geometry already. It's definitely linear, right? Now, one thing you'll see that is that once we have a geometry, even a simple geometry, we can start asking things like, okay, are these guys polar or not, right? Polar. Now remember back to our electronegativity discussion. Electronegativity says whether we have unequal or equal sharing of electrons. Now, for molecular polarity, what we're going to do is look at the poles of the molecule. Look at opposite atoms. It's all about looking at atoms and whether they have partial charges or not on opposite sides. All right. So for example, this is going to be a linear geometry. Is there any electronegativity difference between an N and an N? Well, no, they're the same atom. So this guy is non-polar. Right? It's non-polar. There would be like an equal sharing of electrons. Remember we kind of drew these clouds? The cloud would just look like it's okay, there's the same amount of electrons around each end. There's no unequal sharing. There's equal sharing, so it's non-polar. And that will be the same thing here. All right, O2 is non-polar. What about a situation like CO? All right, well, if we go through and we get the Lewis structure for CO, all right, and let's just do it quickly for practice. We need a total electron count. So carbon has 4 electrons, oxygen has 6 electrons, all right? So we got 10 total electrons. Let's pick carbon as our central atom, all right? So let's connect these up with a single line. So we have 10 total electrons. We're now down to 8 electrons. Where'd they go? 1, 2, 3, 4, 5, 6. On that outside atom that I picked as the oxygen, where do these last 2 go? They go here. This is a single bond right now, okay? So now we're out of electrons, okay? So, all right, well, we're gonna need to bring in some more sharing to satisfy everything. So it looks like carbon, triple bond O to oxygen is CO. Now we can look at this and say, okay, well, what's the geometry? Well, again, this is a really simple case. Well, there's only 2 things attached, so this geometry is definitely linear. Is there electronegativity difference between C and O? And the answer is yes. It's not like N and N or O and O, where there's no electronegativity difference. Here we know that O is closer to F, so it's partially negative. That means that C is partially positive. Now think about like the North and South Pole. They're on the opposite sides of the globe. That's the same thing that you do here. Look at the atoms on the outside, right? Is there one side of the molecule that looks different in charge than the other side of the molecule? And the answer is yes. This molecule down here then is polar. And we don't know polarity until we look at the actual 3D structure. This is a simple 3D structure, but it illustrates the point. One side is positive, one side is negative. There's difference in charge on opposite sides, right? This guy is definitely polar, okay? So let's go to a slightly more complicated example that we already did. And let's look at CO2. And now we'll be getting to information on our chart. Remember the Lewis structure for CO2 was this. Okay? So on our chart, what we would say is, there's a central atom that we're going to call A. And what's attached to it? 2 other atoms. Okay? So this is going to be an X and this is an X. This is then a family. And this particular family is also a linear geometry, right? So this guy is linear as well. So whenever you have a central atom attached to 2 things, and that's what I mean, this is just a general placeholder. This means a central atom attached to 2 other atoms, no matter what, it's linear. And we don't really have to draw this any differently because we already drew it as a line. And this kind of makes sense in terms of valence shell electron repulsion theory. This O and this O, they have these bonding regions here. What are these bonding regions going to want to do? Get as far away from each other as possible. Well, that means they're going to be on opposite sides of the C. And so then what are you left with? You're left with a line. All right. Now let's try to decide if this guy is polar or not. Right? So we look at the structure and you look at each bond separately and try to see if there's electronegativity differences. And the answer is sure. This is going to be partially negative. This is partially positive when I look at that. Oh, and the same thing happens here when I look at that O and that C. Now, here's the thing, right? Remember what it means to be polar. Opposite ends of the molecule, opposite sides, opposite ends of the molecule have to look different in charge. All right, they have to look different in charge. Think about the North and South Pole, opposite ends of the Earth, opposite ends of this molecule. If I look at the ends of the molecule, here's what I see. I see an oxygen over here that's partially negative and an oxygen over here that's partially negative. Well, those look the same, okay? The ends of the molecule have the same charge, so this guy is non-polar. Look at the north and south pole. Look at the opposite ends, right? This guy is the same as this guy. The central atom doesn't matter. It's all about the outside atoms. Look at opposite outside atoms. If they're the same in terms of their partial charges, definitely non-polar, okay? Now, another example, right, that we did was H2CO. We might have written it differently, okay? I do want to point out that this is how your Chem 101 will represent this molecule. And remember, when you're trying to decide central atoms, H's are never central atoms. Okay, so there's one C and one O. Which one do I pick? Whenever in doubt, carbon is a central atom most of the time, okay? So we're going to identify this carbon as a central atom. Even though H is listed first, there's two H's. We would never pick it as a central atom anyway, because H can only have one bond to it, etc. Remember, we came up with this Lewis structure for this species? All right. So let's look at this carbon. How many things are attached to it and how many lone pairs does it have? Well, it has 3 atoms attached to it. It doesn't matter that it has 4 bonds, you count the atoms attached to it. So these 3 bonding spaces, these 3 negative regions are going to spread out to try to get as far away from each other as possible, okay? What ends up happening is they end up making a triangle, all right? They make a triangle in a plane. So this family is called trigonal planar, all right? A trigonal planar family. The other things you'll be asked, besides polarity, and we'll do that in a second just to practice, is bond angle. So if this is a triangle in a plane, then with our geometry knowledge, we know that these bond angles are 120 degrees, not Celsius. 120 degrees in terms of their bond angle, okay? So this angle right here, 120 degrees, because it's making a triangle in a plane. So this means whenever you see a central atom attached to 3 other things, no matter what, right, you're going to have 120 degree bond angles here, and it's going to make a trigonal planar geometry, right? A trigonal planar geometry. For practice, let's do polarity, and let's remind ourselves that polarity matters in terms of opposite ends of the molecule. We just look at opposite ends to determine polarity. These H's would be partially positive relative to this C, because H, remember, is to the left of C, right? O, though, relative to C, is going to be partially negative, right? Now, what do we look at? We don't care about the central atom. We care about opposite sides of the molecule, all right? So here's one side of the molecule. Here's the opposite side. Do I see the same charges or do I see different charges? I see different charges, right? So this guy is polar. This guy is definitely polar. Now, what you'll see on the chart that we have to know, figure 7.19, is that this is not the only thing listed, all right, for that family. Whenever there's 3 things around a central atom, there's 2 different ways we can get that. We can have 3 things around that are atoms, or we could have 1 lone pair and 2 atoms, okay? So in that case, you're going to have a central atom, and you do the Lewis structure. And there's a lone pair up here, and then there's atoms attached, still making that triangle, right? And let me just emphasize the triangle more. Sorry about that. Still making that triangle. Now, these are probably going to be multiple bonds, but remember, that doesn't really matter. What matters is that we have 3 different negative regions that are going to spread out as much as possible, okay? So here's the thing to remember, right? This lone pair, right, it doesn't get considered as part of the geometry. And what I mean by that is we just look at the atoms to determine what the geometry is. So notice this isn't a triangle in a plane anymore. This now looks like a bent shape, right? It looks like kind of a V, like a bent right? Structure, something that was linear, but we bent it down, right? So it has a different geometry name. It's part of that same family, and notice our picture looks a lot the same. Like we kind of draw the family starting point, but then realize that, oh yeah, if I place these lone pairs here, okay, then these lone pairs, right, they're not part of the atom, so I don't consider them as part of the geometry, right, but they are taking up space, right? So this structure gets a different name even though the picture looks similar, right, and this name is bent. The only other thing we have to mention, you can see this indicated in that chart, and that's why this chart is so important, is that these electrons, they really take up a lot of space. They repel more than these bonds do. So what they'll do is they'll actually kind of, all right, repel and push these guys together more than you would expect. So what we mean by that is if this was an AX3, this bond angle would be 120 degrees. And the way that we draw it even is 120 degrees. But what this lone pair does is it actually squeezes these together a little bit more than you would expect. And so this bond angle is actually less than 120 degrees, right? So even though we draw it as 120 degrees, we don't have to get so detailed with our drawings. And Chem 101 is doing the drawing for you anyway. But we have to realize that these guys are actually squished together a little bit more because this lone pair, it doesn't have any atom to balance it out. There's no positive charge. It's just a big chunk of negative. It pushes these guys together, okay? So now this process repeats itself with all other families, right? And I just want to bring up a couple other examples of things that we've done before in terms of Lewis structures and then get to the rest of the chart, all right? After that, we did CH4, and this was our Lewis structure for CH4. It was the first Lewis structure we did. It was a pretty simple Lewis structure. How many things are around that central atom? This has 4 atoms attached to it. It's an AX4. It's a new family called a tetrahedral. This is a really important family because carbons, they have 4 bonds around them. So when they're singly bonded, the 4 things, you see tetrahedral structures. This Lewis structure is not the geometry though. These 4 things are not going to be a square. They want to get away from each other and they have 3 dimensions to do it. So this is how we draw a tetrahedral. And even though Chem 101 is doing the drawing, you still need to know how to draw it yourself in your notebook because other chemistry courses, you might not have Chem 101, right, to use. We draw one up, and the bond angles for a tetrahedral are at 109.5. Now, you don't have to get exact with that 109.5, but notice I'm drawing it more than 90, right, but less than 180. So the bond angle is 109.5. The H's that are left, one's going to be coming out and one's going to be going away. So the way I like to draw that on my paper is the one that's coming out, I draw like a thick, bolded, like almost like an inverted triangle where I try to make this thick here and then skinnier there. And I put my H, and then right behind that I put some dashes. And I tuck behind, all right, this H. So now you can kind of see the structure. This is a tetrahedral. One up in the plane, one also in the plane at 109.5 degrees. The way that I drew this is I find the bisect of this angle, right? And I draw a bold and then I dash behind, okay? And this is the true tetrahedral structure, all right? The bond angles here, I mentioned it before, just gonna say it again, 109.5. What about polarity? Well, we know these H's are partially positive relative to this C. So when we look across that bond, and remember, we gotta look around each bond individually, right? We assign partial charges. Does that C matter? Think about poles. No, the C doesn't matter. Opposite ends of the molecule matter, right? So let's look at this end of the molecule and the opposite end is here, right? Do you see the same charges or do you see different charges? Well, all I see on the outside are H's. Remember, the C really doesn't matter. I have H's on the outside here, H's on the outside here. All the H's are partially positive. So this guy is non-polar, right? Non-polar. Okay. So hopefully you're seeing with these examples how we go through polarity determination. Now, One other example we did, I think we did NF3. And when we came up with a Lewis structure for NF3, we got this. And I'm not going to write the dots on the F, right? Because they honestly don't influence things too much when we're determining structure, right? Now if I look at this, there's still 4 things on that central atom. But stuff has changed, right? This is actually an AEX3, right? An AEX3, right? Still 4 things around the central atom, so what we draw and what the family is, and Chem 101 will ask you for the family. It'll ask you for like the domain name, okay? It'll ask you for what you draw. We draw a tetrahedral, but is it really a tetrahedral anymore? Well, no. I'm going to put my nitrogen in the middle. 1 up. 1 at 109.5. Find the bisect and bold. And then dash behind. Whenever there's 4 things around the central atom, we always draw it the same way. We draw that tetrahedral family. But remember, this lone pair is not part of the structure, so really the structure is down here. And if you connect up these F's, I'm just going to do it in a different color. If you connect up these F's, what you'll see is they make a triangle. And if you connect these F's up to the N, it makes a triangle-based pyramid. So the name for this geometry, the family name is different than the geometry name now. The family's tetrahedral, because that's what we draw. This is a trigonal pyramid. Right? It's a trigonal pyramid. Right? So now, is this guy polar or not? F's are going to be partially negative. The N is going to be partially positive. You look at the atoms again to determine polarity. Here's one end of the molecule. The other end of the molecule's down here. Do you see the same or opposite charges? You see opposite charges. You see different charges. So this guy is polar. Okay. Now we didn't do water together, but let's do water now. When you do H2O, all right, what you get is this Lewis structure. And hopefully you're able to do that yourself and know where that's coming from. Okay, again, I see a central atom. How do I know O is a central atom? H is never a central atom. O showing up by itself. But I see a central atom that has 4 things around it. A, E2, X2. Well, then what do I draw? What's the family? I draw a tetrahedral, right? So I do 1 up, 1 at 109.5. Let's do the H's there. Bisect bold, dash behind. And the last example, in this example, it doesn't matter where you put these dots. I just like to put the dots in regions that let me see the structure more. And so through experience, I know that, okay, I'm going to put the H's in the plane because it'll be easier to see. This is the family, but is it a tetrahedral anymore? No, because we just look at the atoms to determine the family, and now it's bent, right? Right. If I look at H to O to H, it's bent. Right. I didn't mention it with the last example, but the same thing will be here. What's this bond angle? This bond angle, just like the last example, even though I didn't mention it, is less than 109.5 degrees. Less than 109.5 degrees. How do I know it's less than 109.5 degrees? Because the family would give me 109.5, but what do these lone pairs do? They push it together more. Less than 109.5. What about polarity? Partial positive, partial positive, partial negative. Don't look at lone pairs, look at opposite ends of the atoms making up the molecule. This oxygen is negative. The opposite side are these H's that are positive. Is water polar? Yep, but you probably already knew that, but now we can come up with that ourselves. Okay? So this process repeats through that table. Okay, so hopefully you're seeing the pattern here, right? And what I'm going to do now for the rest of the table is just kind of talk about the other structures. And there's one other thing that manifests with these structures that are different than the structures so far. Remember I just said how we don't really care where we put the lone pairs when we go through a family. For these next structures we will. So what about like the AX5 family? This family name, this electron pair domain name, all right, is called a trigonal bipyramid. So whenever there are 5 things around the central atom, we always draw the same thing. We draw the central atom here, all right? And then we make a line, right, to an atom above and an atom below. We then make a T, right, to an atom in the plane. And then the reason it's a trigonal bipyramid is in this plane, there's also a triangle. So there's going to be one coming out. And then we don't tuck this guy behind, but to show it's going away, we do a dash line. And now we can kind of see why we call it a trigonal bipyramid. Here's a triangle, and there's a pyramid up to the top. And there's a pyramid down to the bottom. So it looks like 2 pyramids sandwiched together, right? Trigonal pyramid up and a trigonal pyramid down. So whenever there's 5 things around this, this is a trigonal bipyramid family. This geometry right here is a trigonal bipyramid. And there's actually a bunch of different angles. This angle here is 90 degrees. And what Chem 101 will ask you for these specific angles. This angle here is 180 degrees, right, between these guys. And then this angle here, these are triangles. So in the plane, these angles are 120 degrees. But you see this on your chart. I'm just kind of pointing out why they're showing you what they're showing, all right? Now, everything isn't equivalent. And so what I mean by that is notice there's a bunch of different angles. For a tetrahedral, there's only one angle, 109.5. Now, it could get distorted by a lone pair, but there's one angle no matter where you look. Because there's different angles depending on how you look at this, we give these different labels. I'm going to label these with an AX, the ones that are up and down, because they make an axis. So AX stands for axial. These guys, all right, if this is like the axis, think about an Earth, then these guys are in the plane and these are equatorial. So I give these a label EQ, axial and equatorial. In this family, the thing to remember is that the equatorial positions are where you place pairs. So let's say I do a Lewis structure and I see, okay, there's a central atom. There's one lone pair, and there's 4 atoms attached. Here's the thought process, and make sure you get this down and it makes sense. 5 things are attached to the central atom. So I know what the family is, and I know what I draw. I draw a trigonal bipyramid, okay? But I also know that it's no longer a trigonal bipyramid. I know that if one of these guys is replaced with a lone pair, right? And I replace the equatorial positions first. Now the structure, right, the actual geometry is based on what the atoms are. The atoms have this shape, which we call a seesaw. Right? It's a seesaw shape, okay? Because it looks like if somebody was sitting here and somebody was sitting here, they could kind of bounce back and forth, all right, between, all right, like a maximum here and a maximum there. It looks like a seesaw shape, okay? What about if I do an analysis and I see that there are 2 lone pairs on my central atom and 3 atoms attached to it? All right, I know I'm a trigonal bipyramid family. I draw the family shape. Then I remember that for this family, all right, and I'm just going to switch up the position of this. For this family, I pick any equatorial position I want and I put my lone pairs there. So I'm going to put a lone pair here and a lone pair there. And I'm going to keep this as an XEQ. Okay, so I drew the family correctly, all right? But now, all right, I see that the shape that's being made with the atoms is a T. So this is a T shape, right? What about these bond angles? Are these bond angles distorted away from what they would normally be? This would normally be 180, but what are these guys doing? They're pushing them together, so it's actually less than 180. This would normally be 90, but what do these lone pairs do? That's the same no matter what. These lone pairs squish things together to make them less than what you expect. So this would be 90, but it looks actually like it's less than 90. Okay. And then finally, what happens if I do an analysis and I see that there are 3 lone pairs attached to the central atom, right? And 2 atoms attached to the central atom. Well, I know the lone pairs go equatorial, and now what shape is that? It's a line. Now, even though these lone pairs distort, if I get pushes from this direction, they're counteracted by this direction. So this, all right, line, right, only has one angle, 180 degrees, right? So the distortions that occur, they cancel out in this instance, okay? So hopefully you see the idea here. We have a family, we know the family name. If there's just x's, the family name is the geometry name, okay? Once we place e's on it, all right, we get different, all right, geometries. Here we see that we have this line, we have a linear geometry because the geometry is only determined by the atom shape, all right, not where those lone pairs are. Okay. So there's one more family than to talk about this semester, and this is the AX6 family, and we're going to do the same thing. And you'll notice that all we're doing is really going through that chart. Right? Now remember, at the end of a problem, you're going to have to put like the actual atoms there, analyze bond angles, analyze polarity, but you do that the same way that we were doing those examples in the beginning, okay? So nothing changes there, it's just these are where these drawings are coming from. That's what we're indicating now. So if we have an AX6 family, right, we call that an octahedral, and we draw that like this, right? Put the central atom in the middle, one up and one down as axials again. And what we make in the middle now is a square. So instead of having equatorial positions that all make a square, these equatorial x's, instead of having these equatorial positions that make a triangle, these equatorial x's, when there are 6 things around a central atom, okay, they make a square. And the reason it's called an octahedral is that if you like make a triangle between the outside x's, there's actually 8 faces. And if you've ever seen an 8-sided die, that's what this is actually making. It's making that octahedral shape. So this is the family and this is the geometry, all right, for this particular structure because there are no e's there, okay? So what are the bond angles? X-ax, A to X-ax, you can see is 180. X-ax, A to XEQ is 90. XEQ, A to XEQ is 90, right? So what happens if I look at my structure and I see one lone pair and 5 atoms? All right, E plus X is 6, so what do I draw? I draw this. And then what we remember for this structure family is we replace axial positions first. So the axial position is replaced here, right? Now if I look at this, I have a square that I can make a pyramid with this top x with, right? So this is a square-based pyramid or square pyramidal or just square pyramid, right? Square pyramid tells the shape. Keep going with what we've been doing. A, E2, X4, E plus S is 6. So I draw this structure. I replace axials first for this family. It's different than another family, right? These guys distort bond angles, right? But now for this case, the bond angles would be canceled out in terms of the distortions. This guy, all right, is square planar. It looks like a square in a plane. It's a square planar. Now these guys, like I said before, do distort. So the last example where there's X up here, this guy would push everything up. But as this pushes up, this pushes down now. So it's like that other case where these guys do distort, but if they push from opposite directions, right, the bond angles aren't distorted. So XEQ, A to XEQ is 90 degrees. And that's why we say it makes a square. Okay, square planar. You can keep going, right? Now we only have XEQs to replace. So what about AE3, X3? Again, all right, E plus X is 6, so we would draw this picture, and what do the atoms make now? They make a T shape, okay? And hopefully you're seeing everything here. What happens if we have AE4, X2, just to finish out your chart, right? Now again, we have a bent shape, okay? We have a bent shape. So the things you have to do is you have to be able to draw these structures with Chem 101, but Chem 101 does it automatically. But recognize where they're coming from, okay? Be able to link the structures you see with Chem 101 to this chart. In subsequent chemistry courses, you have to draw these yourself, so always remember that you'll have these in your notes with how to draw them, how to think about the shapes, right? What Chem 101 won't show you is whether they're polar or not. And that's where being able to draw these on your paper and do that analysis that I talked about comes into play. All right. Look for electronegativity differences across bonds, and then look for opposite ends of the atoms. Look for opposite ends of the molecule, just looking at the atom parts. Opposite ends of the shape. And if you see difference in charge, then it's polar. If you see the same charge, then it's non-polar. Okay? Always remember, what you have to do is look at that figure 7.19 and go there, all right? Get all that down in your notes, and then you have everything you need to know about geometry. Okay? As always, practice, give me questions, all right? And good luck on your final, and good luck with finishing out this homework. This is actually the last topic that we'll talk about. So, keep up the good work, keep up with your motivation, finish strong, and as always, lean on me for any help that you need.